Good afternoon. My name is Mary Couture, and I am a junior majoring in mathematics, working with Dr. Kyungyong Lee in the Department of Mathematics. We are working on searching for patterns in cluster scattering coefficient sequences. Don't worry, by the end of this talk, I promise you'll even understand what that title means. So we're going to begin with a brief overview of the topic so that we situate ourselves and understand the mathematics that we're working with. We will then discuss a characterization of the scattering diagrams from which the coefficient sequences arise. We will discuss some previous work that has been done in this field, and then we will discuss our work in the form of limit derivations. A bit of background on cluster algebras. They are a mathematical construct first defined in 2001 by Sergei Fomin and Andrei Zelevinsky, and they form a connection between theoretical physics, particularly quantum field theory, and many other areas of mathematics, not least of which are algebraic geometry, graph theory, and representation theory. Here we will focus on one particular substructure, but cluster algebras as a whole are an incredibly active area of mathematical research. With that in mind, we will spend a little time defining what cluster algebras actually are so that we can understand their scattering coefficient sequences. When you look at this diagram, you can think of the cluster algebra fairly simply as the blue dots that are on the broken line graph. The scattering diagrams are then the rays that pass through those dots. Now, the coefficients of the dots are important and do define what the cluster algebra is. So you really can think about this as the Cartesian plane passing through lattice points, which have integer coefficients. What a cluster algebra actually is, though, is a set of integer coefficient polynomials alongside a rule called mutation for generating more elements. There's an example of this up on the board. We start with the polynomials x and y, and using the rule, we can generate further elements in the cluster algebra. A scattering diagram can be used to characterize each of those elements, and there are an infinite number. What is a scattering diagram itself, though? If the cluster algebra elements are polynomials, then the scattering diagrams are a combination of an infinite number of polynomials along a ray. And so we can describe them as infinite polynomial sums. The coefficients of the polynomials themselves in a diagram are called cluster scattering coefficients. We have an example on the screen here of the coefficient sequence for the cluster algebra element corresponding to b equals 3, c equals 3, which you can think about as the point on the Cartesian plane. Previous work has discussed many properties of scattering diagrams, several of which we use here. First, Elgin et al. Have described formulae for the coefficients of very specific scattering polynomials. These formulae are somewhat difficult to derive, and so the ones that we have are fascinating and the topic of this research. Second, Lee et al. Have described a link between the coefficient of any given part of a cluster scattering diagram and the number of tight gradings possible on a grid of a given size, determined by where on what scattering diagram it is. So both how far along the ray and what lattice point the ray originally passes through. Our work looks to combine the speed of Elgin's formulae with the general applicability of Lee's tight gradings. In this way, we hope eventually to gain many formulae without the intense combinatorial calculation necessary for tight gradings, which are a further relation to theoretical physics and describe the combinatorial state of an object, the state in which it can be positioned. The major results of our work are first, a generalized limit value for a particular type of lattice point, as described by Elgin et al. Second, MATLAB code that can quickly and efficiently calculate ratios between coefficients. And finally, the information that these coefficients approach exponential growth for a particular example of the Elgin formulae. We begin with the limits of sequences. As a brief review, if you don't remember your calculus 2 at the moment, A limit is the value that a sequence takes as its index approaches infinity in this case. We refer to the coefficient as tau, and we look at the II implementation of tau. So we're looking effectively along the line x equals y here. An example of this that is similar to what we deal with, because it is geometric, is the sequence 2 to the n, which approaches infinity as n approaches infinity, but the ratio between these two terms is always 2. What we considered was the ratio test on the following formula for tau given by Elgin et al. Tau of II is the greatest common divisor of b and c divided by a function of b and c times I plus that greatest common divisor multiplied by the binomial expansion of the expression there. This is actually a factorial when you write it out, and so it becomes incredibly computationally complex incredibly quickly. Working with it analytically, the ratio test simply informs us that the sequence does not converge because at any point the ratio is greater than 1. The limit approaches a constant value, however. And that tells us that our coefficient sequence can be approximated by a geometric sequence. We're going to approach exponential behavior as we approach infinity. This is fascinating because it's highly symmetric behavior. And further, if you look at the final ratio which we managed to derive for this formula, you can see the degree to which it is incredibly and beautifully symmetric. We, however, needed to write this in MATLAB because simply working on a piece of paper was entertaining but less effective for calculating things at several thousand. The formulae for Elgin et al. To calculate directly require very large numbers because of these factorials that exceed reasonable computer memory. To calculate the ratios at a known point, then, we derived a simplified product expression of the ratio and continued to take the limit only of the ratio. Some example calculations for how we considered this are presented here. And in the b equals 3, c equals 3 case, you can see that we approach about 9.5. And indeed, we graphed this in MATLAB, and you can see in both b equals 3, c equals 3, and b equals 3, c equals 2, this very nice approach to the constant. This is the graph of the ratio as you increase I. In the future, we will use this small selection of limits, which we have derived, to start looking for more sequences of tight gradings. We will finish the limit derivations for all of the formulae given by Elgin et al., and then we will implement GPU computation techniques on previously written code for computing the number of tight gradings. This will allow us to begin effectively computing the coefficient sequences without a formula. We then hope to take those strings of coefficients and analyze them to form our own formulae, and then the cycle can repeat, thus allowing us a better and quicker understanding of this fascinating subfield of a quickly growing area of mathematical research. Are there any questions?
And just, maybe you can help me clarify this. Your earlier slide, you were describing the cluster algebras in maybe a two-dimensional context. Are there such things as three-dimensional cluster algebras, or does that question even make sense?
I understand what you're saying, yes. So we are not working, I do not believe there is such a thing, and the work that we are doing with Elgin's formulae certainly do not consider such a thing. I would not say that such a thing is possible because of the structure of tight gradings, which are two-dimensional objects. What you actually get, if we head back to the graph, when you see that point that looks like a point on the Cartesian plane, the axes are determined by a polynomial expression, 1 plus x to the b along the x-axis, what we would call the x-axis, and 1 plus y to the c along the supposed y-axis. And so b and c are the exponentials in the polynomials themselves. Because we're expressing this only in x and y and in b and c, we're not considering a third degree of freedom. And I, in my work that I have done in literature review, have not seen a third dimension appear anywhere.
You mentioned potential applications of clustering algebras to theoretical physics in terms of like probability distributions. Are you talking about like on a quantum mechanical sense?
Yes, we are.
So you described the cluster scattering diagram as rays, but you have different sequences for lattice points on the same ray. Would you mind elaborating on how that works?
Absolutely. So the point, the b and c coefficients are not scaled linearly. Those are actually very distinct elements in the cluster algebra. And so they would not behave remotely similarly, and we can treat them as separate objects.
Yeah, I'm just curious. How do you know how many tight gradings there are?
We have previously completed work by Lee et al. That has written code that can perform the intense combinatorial calculations required to determine the number of tight gradings at a point. It is an arrangement of blocks in a grid under specific rules, is what that actually forms.